Investigating the relationship between force and energy. Morgan Henry, Amelia Schroeder, and Sophia Sogensand, Group 6B.
Introduction. Our question, how would changing the force pulling on an IO lab cart change its kinetic energy? Our hypothesis. If you pull on the IO lab cart with a greater force by increasing the mass of the weight acting on it, it will have a greater kinetic energy, thus a greater amount of work. Our main findings. A greater force applied to the IO lab cart led to a greater kinetic energy of the cart. Why we care. We were able to relate force, potential energy, work, and kinetic energy. Our system schema included the earth, the string, the weight, the pulley, and the IO lab. These interacted through force of gravity, force of tension, and force of contact. Our energy pie charts for the IO lab had potential energy slowly transferring to kinetic energy. The pie chart of the weight was similar. The free body force diagram of the IO lab had the normal force of the table on the IO lab, the force of gravity of the earth on the IO lab, the force of tension from the weight on the IO lab. The weight had force of tension from the IO lab on the weight and the force of gravity of the earth on the weight.
For our experimental design, we first started out by calibrating the IO lab. We set up a pulley system to the table and attached the IO lab to the pulley with the string. At the end of the string, we attached a mass. The mass was increased each trial from 50 grams to 100 to 200. We released the IO lab while recording a video to use for Tracker, and we collected force versus time graphs. We also analyzed the videos using Tracker to find values of velocity for each trial. We found the value of work for each trial from work equals change in kinetic energy. One main physics idea is work. Work can be found by two equations. Work equals force times distance, and work equals change in kinetic energy. Work is the transfer of energy across your defined system's boundary. Must have this interaction in order for work to be done. The work energy theorem allows the examination of forces from Newton's second law to connect to an object's quantity of motion to the concept of energy. The equation translates to work equals change in kinetic energy. It tells us how speed changes and is independent of direction. Another main physics idea is force. Force is found by mass times acceleration. That's the net force, which is the sum of all forces acting on the system. The force of gravity can be found by force equals mass times the gravity constant. Force is a vector that quantifies the interactions between two objects. Force can be attributed to weight, normal force, tension, and surface friction. Common patterns with force are increase in mass causes an increase in force, and force is proportional to acceleration.
Force graphs produced from the IO lab. For the 50-gram drop, the force for this ranged between 3 and -3 newtons. For the 100-gram drop, the force ranged between 5 and -3 newtons. And for the 200-gram drop, the force ranged between 6 and -3 newtons. Another main physics idea is kinetic energy. Kinetic energy equals 1/2 mv squared. The definition is the measurement of how much an object is moving. Kinetic energy can never be negative. Change in kinetic energy is defined as work. Change in kinetic energy is also related to how far an object has traveled when that object is in free fall motion. Our results produced a kinetic energy of 173.01 joules for the mass of 50 grams. For the mass of 100 grams, we had 348.24 joules, and for the mass of 200 grams, the kinetic energy equaled 457.54 joules. Work equals delta KE as shown by the work energy theorem. As shown from the results above, as weight increases, therefore increasing the force pulling on the IO lab, kinetic energy of the IO lab increases as well. Same. Sources of error. Issues with the tracker, calibrated IO lab incorrectly, variations of height at which the weight started before the IO lab was released, and increments of weights being too large.